Okay, who still needs a handout? It's going so slowly. Okay. How's that? How's that? Fell off my face. All right. Who needs one still? Yes. Here. I'll just take all of those. Here. Here you go. Enjoy your burrito or whatever. Sorry? It's a new handout. It's even better than the last one. Here, take a bunch. Here you go. Take some. Who doesn't have one? Just throw it at somebody. Do you have enough? Okay. Who doesn't have one? Still don't have them over here. That's a tough break. One more? Oh, look, he's giving them out. There you go. Ah, here. There you go. All right. Who doesn't have one? You do. Okay. Chaos at the beginning. Chaos throughout. They're all gone. Where are they? Who has extra? Send them down this way. Oh, there you go. Right there. Boom. Thank you. Thank you. Oh, thank you so much. This is a new handout. Yes. Yeah. Applause. Yeah. Thank you. Yeah. Very nice. Yeah, exactly. Tip your hat. Okay. We ready to go? Hello. Hello. Waiting. Waiting in the front. Okay. Thank you. Okay. So we continue our discussion of concurrency. What did we talk about so far? We talked about locks and um, specifically how this relates to atomicity, avoiding data races around critical sections and all the problems that ensue there. We talked about our other fundamental primitive, condition variables. And these really relate to ordering problems where you want one thread to do something before some other thread does something. And we saw simple examples of that, which were things like the fork join problem, like waiting. Remember when you create a thread, you can consider that like forking a thread. And when you wait for it, it's called like to join a thread. It's just historical terminology. And that waiting for a thread to complete, for a child thread to complete, that's a simple ordering problem. I want to launch this thread, have it run, and then wait for it to complete. Now, of course, that isn't generally, you don't generally just launch one thread and then wait for it to complete, because there's a more efficient way to do that. What's a more efficient way to just launch some code and then wait for it to complete than creating a thread? What's more efficient than that? A function call. Yeah, we can just call a function call, right? That's much cheaper, much faster. So usually what you do is you create a bunch of threads and wait for them to complete, or have some threads go off and do something else while you do something and then wait for them to complete. But that's that fork join problem, and it's absolutely an ordering problem. We also saw a very complex example, which 100% you're going to need to understand because it's just such a well-used kind of pattern of concurrency, which is the producer-consumer problem. That was the case where we had a bunch of producer threads, whatever these threads are, and they were putting data into some kind of shared buffer. And then we had some consumer threads, and what they were doing is pulling data out of this shared buffer. And this is a bounded buffer, which means it's of a fixed size. And we saw that that was a complex ordering and atomicity kind of problem going on there, right? There was ordering that producers had to wait for there to be room to put something in. Consumers had to wait for something to be produced in order to pull it out. And then there was an atomicity issue because there's a shared queue, right? A shared queue sitting between producers and consumers. And so why do we study these interactions? Well, mostly because you don't want to generally be writing, like you don't want to come into some concurrent program and then just make up some code and hope that it's right. It's really hard to write correct concurrent code. So what we do is we study working examples of common patterns, and normally we use those or some slight variation of those. And anytime you're introducing concurrency into some program that you're dealing with, you should be very paranoid about it. You should say, hey, how can I use an existing solution if I can? If you have to do something that feels new, you have to think through it very carefully and really analyze it. It's very tough. There's actually a bunch of tools that people use, and even there, it's still very challenging. So that's what we've looked at so far. And to some extent, that's all you need. If you understand threads and how to use locks and how to use condition variables, you're kind of fully functional. But today we're going to talk about a new primitive, which is called, today's what's new thing is going to be called, it's called a semaphore. And you can think of it as it's kind of like a lock and a CV, condition variable, in one. So it doesn't really add some new capability. Sorry, is there a question? No. So it doesn't add a new capability. So then you might be wondering, well, why are we talking about it? Like, we already have locks and condition variables, and that's kind of good enough. There's a few reasons we talk about it. One, it's historically interesting. So in the very earliest papers that were about the very earliest research about concurrency, going back to Edgar Dijkstra, who first thought very deeply about a lot of these problems, or was at least an early thinker in this space, he thought about a semaphore. That was, in fact, the primitive he used in some of these early papers he wrote about how to build operating systems correctly. So it has a historical significance, but even that's not that great. Perhaps more relevantly, a lot of times, like when you have an interview for a tech interview, which you will have in your life if you decide to become gainfully employed, which many of you will, often people will just ask questions about semaphores because that's just something that's been around forever. So it's good to know from a tech interview way. And also simply, sometimes it's just very natural to use semaphores. It's just kind of, we'll see some code examples and why they're just kind of sometimes a little bit more natural than using a lock and a condition variable. But really, they are the same thing. We can use semaphores or we can use locks and condition variables. And there's no problem that one can solve that the other cannot solve. They're equivalent. Make sense? Any questions about that? Cool. All right, so you have a handout. Does everybody have a handout? Asking now again, handout. Let's look at the handout. I will bring the handout up here. I'll move this over a little bit. Let's look at the definition first. So we're going to have semaphore. You can think of an abstract object, a semaphore, and these are available in some operating systems provide semaphores, like Linux has them. Some other systems have them. Not every system has them. You can do three things to a semaphore. You can initialize it. Each semaphore has some value associated with it that's kind of built in. That's very similar to that state variable that we often use in conjunction with a condition variable, if you recall. So it's very similar. So it's a built-in. It just has a value. And you can see that right here. So you initialize it with some value. And then there's just two routines, which also have a familiarity to what we've seen before, except they have a little more function to them than a condition variable. So what wait does is it checks if the value is non-positive. And if the value of the semaphore is non-positive, it puts itself to sleep. Okay? If it is positive, then what it does is it doesn't put itself to sleep and then decrements the value by whatever. So you can have whatever initial value you want, but when you then call wait, you will either go to sleep or you'll decrement the value. And after you're woken up, you may then decrement the value, as this little code segment shows. Now, this is just a logical definition. We're not showing like how this is built. You can imagine there's some concurrency issues around building a semaphore. We'll talk about that maybe at the end of today if we have enough time. But you can think of these as like being atomic pieces of code. Like whoever's implementing the semaphore is going to make sure that there's only one thread active inside the wait or post at a time. There's another routine which is called post, which is a little bit more like signaling, and they just called this for historic reasons. And that increments the value, and then if there is a waiting thread, much like before, it wakes one. If there isn't one, then it doesn't. So that's the definition. And of course, we have to kind of let that sit in our heads. And I guess a fourth reason that, we talk about semaphores is there's just really many books of logical concurrency problems that are built, solutions are built using semaphores. So there's one, um, an old a person I knew, Alan Downey from way back in graduate school. He has a book called like the Little Book of Semaphores. It's just all concurrency problems, all written using semaphores to solve them. So there's just many example problems out there that if you're interested in, they're kind of fun to do. I mean, as fun as concurrency problems get. That's about how fun they are. But there's still a lot of them out there, so it's good to understand how they work. So that's the basic definition. Yeah, question. Yeah, why are they called semaphores? Why did Dijkstra call them semaphores? It relates to like signaling. Like there's the terms in like aviation that a semaphore has to do with signaling and flags, right? So it has to do kind of with signaling. And if you remember with condition variables, we talked about signaling and weighting. So it kind of relates to that, but it's kind of a weird name, admittedly. Sometimes people just invent a name for something and it sticks. But yeah, it's a little bit of a strange name. In fact, I mean, the original names around these things were like in Dutch. So I'm not sure like the translations even make that much sense. But you know, like in the early days of computing, right? The very early days, a lot of the early work was done in Europe, like in the Netherlands and England, certainly, very pioneering work. And then, the U.S. industry kind of took off, and then, ever since many years, that was kind of the U.S. became the center of the computing world. But a lot of this very early work you'll see coming a little bit more from abroad. And now, of course, it's much more international, and inventions come from all over the place. Okay, so now what we're going to do is we're just going to, and you're going to do this work because that's what we do in class. So you do a little bit of work. Is we're going to look at some of these traditional problems and a couple new problems, and try to understand how to use semaphores to solve those problems. Right. So you have in front of you, you have the definition, which you can stare at. And the first thing you have to do here, let's just look at this code here, the mutual exclusion problem. So this is a problem around atomicity. Here we're initializing a semaphore. And as always, remember, with locks, with condition variables, with semaphores, you have to initialize them before using them. Otherwise, the code might run, but it might not do what you expect. So you have to be careful to remember to do that. And you always do that really before the threads start running. And then here we just create some number of threads that run this worker routine. And you can see we're doing the same old boring thing, like updating a counter repeatedly in a loop. So this we know when we see like a counter getting updated by a worker, and the fact that there's a loop doesn't really matter here. Let's say we're just having each thread update the counter once. It doesn't matter. It's a critical section. We have to be worried about the data race condition. So what we're trying to do here is add some code up here that basically uses a semaphore as a lock. So how do we use a semaphore as a lock? And to do that, you have to use wait and post in some way up here, and you have to initialize the semaphore, which we call lock, to the right value. And then you can see this code creates a bunch of workers and then join waits for them to complete. That's all that code does down here. So spend like 3 minutes, 4 minutes talking about how do you use wait and post up here, and what initial value do you put here so that the semaphore behaves correctly as a lock. Okay, and feel free to talk to your neighbors. Does anyone need a handout still? Handout? Handout, yeah. Handout? Yeah. Only in the back row. How's it going? Sure. No, no problem. Going? All right. Oh, you want one too? Gotta raise your hand higher. Oh, here you go. Yeah, sure. All good. Just wakes one. No, it's probably a queue, but you know. All right, let's recenter here. Thank you. So we have to think about a couple things in this code. Let me do that right here. First, we have our code that we have to surround. We have a critical section, right? We have some critical section. Critical section is that part of the code that if we don't think about locking around it, it's going to execute in a funny, non-deterministic way. It's indeterminate, right? Our update of our counter, as we see over here, is one such piece of code, right? For example, counter plus plus. So we have to put something around our critical section. Now, before we would, for example, put a lock and unlock, and that was obviously very simple to do. There's nothing complicated about that, and it eases all your concerns around it. So what we need is the functional equivalent of this, but using a semaphore. So this is the, oh, sorry, thank you. It's dramatic, it's hidden. The lock version here is just putting a lock and an unlock around our critical section, or lock acquire, lock release, right? Either way, you can call it whatever you want. And then in the semaphore version, we're going to do the same thing. We have our critical section, which is this counter being updated in a loop. And this is not an interesting parallel program, but that's okay. And what we're trying to do is put something above it and below it so that the code executes correctly. Now, one way to think about this, immediately to know how to kind of use wait and post around a critical section, is, well, you know one thing that's true. When you're entering a critical section, when many threads enter a critical section, what do you want to do? What do you want to have happen? When many threads are trying to enter a critical section at the same time, what do you want to have happen? Yeah, only one can enter, right? You only want one to enter, and what are the rest going to do? What are the rest going to do? They're going to wait. So immediately, like this name is kind of a giveaway, but also if you think about wait versus post, like there's no way this post routine is ever waiting for anything, right? That's never going to wait for anything. So post is used to signal something to a waiter. So if we're entering a critical section and we want only one thread to enter, we have to obviously put a sem wait above the critical section. And I guess in this piece of code, we're using a, the lock. It's called, the address is called lock. And then we're going to, this is an ampersand in kind of bad form. And then we'll put a post afterwards. So this is how we do the same thing using semaphores. The critical thing, of course, is the initialization. And to use a semaphore, I'm going to run out of room there. Let me do this. To use a semaphore as a lock, we initialize it to fill in the blank. What do we initialize it to? 1. That's right. We initialize it to the number 1. And let's think about why that is. And the way you can think about that is you can just remember it, like in the future. That's a form of knowledge, right? Like you can figure it out, or later you can just remember it. And either way, you kind of seem like you get it right. So if you fail to be able to figure it out, at least remember when I'm using a semaphore as a lock, just initialize it to 1. It's called a binary semaphore for historical reasons. But let's think about, we can actually derive that, right? And the way we can derive it is we know, let's just imagine the case where we have a single thread entering this critical section. When we have a single thread entering, then we know that we want it to acquire the lock. In other words, it needs to go into wait above the critical section, which is here. We need it to go into wait and then return from wait. We don't want it to get stuck in wait. So we know immediately by thinking about that, that the value has to be greater than 0 at the beginning. Otherwise, it'll get stuck and put itself to sleep. So we can immediately conclude it has to be greater than 0, the value. You can also immediately conclude it has to be exactly 1 by thinking what would happen if we have the case, let's say we have let's say a red thread. Let's say a red thread enters and acquires the lock, and it's running in the critical section, but it hasn't yet released the lock. We want to make sure that if another thread tries to enter, let's say a different color thread tries, scoot that over, tries to acquire, then it needs to wait, right? If while we're in the critical section here, and this blue thread tries to acquire the lock, it needs to wait. And so at that point, what you know is if we need to get this code to go to sleep, it had to have gone from 1 to 0. If it went, for example, from 2 to 1, then the next thread would enter as well. And then suddenly you'd have 2 threads inside the critical section. So by kind of just thinking through the definition of the semaphore, you can see that the value must be 1. And like I said, that's a binary semaphore, it's sometimes called, because it goes really, you can think of it as kind of going from 1 to 0 and back. So semaphore as a lock. Now you can also think through what happens when a thread or some number of threads are waiting. Let's say another case that we want to think about, just really quickly, is there's many threads trying to acquire at the same time. Right, so when we're in that kind of situation, what we can do is we can simply think about what would happen, right? So one thread would acquire, And then the rest, we want to get stuck waiting, of course. And that's totally fine. And then what's going to happen is when one, the thread that is acquiring the lock, right, um, gets through the critical section, it's going to call post. So then what we do is we look at what happens when we call post. And you can see what post does. It's going to change the value from, remember it was 1, then it went to 0. It's going to change the value back to 1. And then what it's going to do is wake one waiting thread. So it's just going to hand off the lock to basically the next thread that's in there. So this acquires, and then when this is releasing the lock, it's going to, wake one of these. Sorry, I'm going to do that a lot today. That's going to be my thing, and you're going to get annoyed. Okay, my apology. Just feel free to yell like that. Yeah.
So in a system with multiple cores, is it possible for like all of the cores to like run the while loop at the same time and they all see that value is equal to 1, so then they all pass?
Yeah, so no. So this is, like I said, this isn't showing how the semaphore is implemented. So we're making sure that like it's implemented correctly. And correctly would mean essentially that if they're all examining some value it's essentially inside the semaphore, it's kind of like a critical section, which means how would you implement it? Well, you'd kind of use a lock around that to make sure that when you're checking it, that only one checks it at a time and then goes to sleep, and then the next one would check and go to sleep, and so forth and so forth. And we'll see how to do that a little bit later. Yeah. No, that's not a dumb question. So I think we're showing a case here, right, where we're often looking at cases where there's some piece of code and it's protected by like one lock, right? But there's definitely cases where locks are used around similar pieces, different pieces of code that are kind of connected. So that certainly is the case, and to some extent we saw that a little bit in that producer consumer problem last time when you think about getting and putting it. Because what's interesting there is the shared data structure, right? So like a queue. But when you're getting or putting from it, you're going to want to put a lock around that, and that's different code, right? So we often look at cases which are the simpler cases, which is like here's the same piece of code. Eventually, we'll look at some even more complex cases where you have multiple locks and things like that. We'll do that a little bit next time. But no, there's no particular reason like that. We're just looking at very simplified cases so we get the basics, and then in real code you have a little bit more sophistication. Okay, other questions? Make sense? So pretty simple. Like a semaphore, you can use it as a lock. Okay, let's look at the next example real quick. This is again the fork join problem, then we'll look at some new problems. Fork join problem is, as we said, just to define it, we have initialized the semaphore, then we create a thread called the child thread. And what we want to do in the fork join problem is have the child thread run to completion before the parent thread then can continue. So the parent creates the thread. It's kind of like a function call, but a very expensive one. And so your job is to figure out where the wait and the post go, and then what the semaphore should be initialized to. Same exact challenge. So again, spend a few minutes thinking about that and talking through it, please. Okay. Okay. All right, why don't we talk together here for a second? Very exciting, less exciting than talking to each other. Sorry about that. So we have our two questions here that we have to answer. One is uh, basically how to use wait and post in these two usages, and then how to initialize the semaphore. Um, I don't know how to spell pthread. Look, that looked a little funny to me. Uh, that would not compile. So pthread. Um, you can rely on the compiler to check your spelling. So in any case, like I don't know what happened there. Um, in any case, when we're trying to think about this, immediately we think, where is the like opportunity for waiting? Where is the opportunity for sleeping? So is it in the parent or is it in the child? Who's going to be waiting? The parent, right? The parent's naturally potentially waiting for the child to complete. So it's very natural to think about the wait happening here, and then the child to have some code that runs, and then to do the post here. And I guess I should put the ampersand s inside of there. Our semaphore. That's too crowded. Apologies. So then the only other question we have, again, is what the initial value is. I suspect you figured this out. But again, you can think about it just by thinking through some of the cases that could be happening here. So let's say we have a case, there's an obvious case that could happen at first, which is that the parent, and this would be a common case actually, is the parent creates the thread and then immediately runs that next line of code, which is to wait. So the parent creates a child before the child even runs, we call wait, right? So let's think about that. We'll call that the parent runs first, before the child even runs. And we want it to wait. So what value does it have to be in order for us to wait? Yeah, 0, right? It's pretty natural for it to be 0. And so if it's 0, what'll happen is the first time the parent calls wait, it'll say, oh, is it less than or equal to 0? Well, it's 0, so yes, so it puts itself to sleep. And that's exactly what we want. The child has not run yet. Then when the child runs and calls post, it's going to increment the value to 1, and then it's going to wake one waiting thread, and that is indeed the parent thread. So that looks correct. You can also think of the case, so that looks good if you think about the cases. You can also think about the case where the child runs first. In the child runs first case, what we have in looking down at this code here, I guess I can just look at it here, sorry. I'll just look at it on here. If the child runs first, that means we're going to call post right away, right? Before this happens, what we'll do is we will call post, right? So the post happens first. So if the initial value is 0, the post will increment it to a 1. So now it's a 1, and it'll call wake one waiting, one waiting thread. Are there any waiting threads at that point? No, but that's okay. The value, we've recorded in the value that the thing we want to have happened has happened. So that's become the value 1. Then when the wait occurs, the wait checks is the value, less than or equal to 0. It's not. So then it decrements the value back to 0, and then it continues. So the wait returns immediately because the child has already run, right? So this case also works fine. So you can see in these two simple cases, you can use semaphores, both as a lock and as a condition variable. And it works, it's very seamless. And in fact, if you compare, like, let's look at this code here. You just put a post, you put a wait, and you initialize this value. And remember what we looked at last time. Let's look at, yeah, I don't know what's going on out there. It's pretty exciting. It's always something exciting in psychology. It's like, this is not what I want to do. Let's just look at Emacs. Let's look at the PDF. This should be obvious to everybody. As you can see here, no, I don't know why I did that. So anyway, it's kind of cool to look at. PDF is actually very easy to understand, but it's compressed, and that's why those bunch of, like, it looks pretty random, but it's actually just compressed sequences. And if you look at PDF and you decompress it, it actually has roots in this programming language called PostScript, and PostScript is this little drawing language. It's a very cool language. I've spent a lot of time mucking around with PostScript in my life. So if you're ever interested, Well, I don't know. Talk to me about it. Literally, no one's ever going to take me up on that. So, so what were we looking at last time? Okay. Um, I wanted to look at a simpler example, actually. Oh no, we'll look at 12. Yeah, sorry. What was I looking at? Oh, I was looking at this. Sorry. And why am I doing that? Oh, for God's sake. Okay, so remember here we were solving the fork join problem with lock and condition variable, right? Those are paired, right? Lock condition variable and a state variable which was done. And you can see what that code looks like. Like after the child runs, this is what it does. It calls lock and done equals 1 and signal. And here to wait, we call lock. We do a little loop. We unlock. You contrast that to why it's like, why do people like semaphores? Well, look how simple this is. It's kind of somebody's already packaged that up for you and made it really easy to just call wait or post and use it in that style. So that's, I think, why sometimes people find them a little bit elegant because they make the code a little bit simpler. Now, of course, you can encapsulate that. We talked about that a little bit last time. You can write some code that makes it look like that, like the condition variable lock look like that. And indeed, that's what, to some extent, that's what the semaphore is. Okay, any questions about that? Make sense? Okay, so let's take a break. We'll come back, talk a little bit more about semaphores and other stuff coming up in class.